So we're going to talk about analysis of covariance. We're going to use the Chow data set. In the model for analysis of covariance, we have a continuous outcome variable, y, equals a, the intercept, plus a covariate. The outcome is 5-year axial length growth. The covariate is going to be the baseline, and the group is going to be, we'll do lens type 2. Let's do lens type 1. Doesn't really matter. We'll do lens type 1, or lens type. And we should check assumptions, the main one being the baseline correlated with the outcome variable. Are those lines that are produced, are they parallel? We've shown how to do that in previous videos, so we're not going to cover that right now. We're just going to go ahead and do the analysis of covariance so we can get into the real purpose of today's talk, which is expected means, calculating effect size, and drawing graphs with confidence intervals. So our outcome variable is axial length 5. Covariate goes down in covariate. Covariates are continuous variables usually. And the group, the only real difference between this and a regression equation is it lets you have factors that are not continuous. And under options, we're going to select our means and compare our main effects.
Is it lens type 1 or 2?
This is just lens type. There is no 1. I say 1 sometimes, but as opposed to 2. We can do, would you rather do 2?
Yes.
Oh, okay. Yes, well, that's kind of cheating, but that's okay. Let's go over here. All right. Options. This actually works better because the assumptions of the parallel lines are met with lens type 2 where they aren't with the other one. Okay, options. I got that. Oh, now because we have a covariate, we don't get information on this covariate unless we ask for the parameter estimates. And that gives us regression, the regression parameter of for every unit increase of baseline, what do we get in the change in axial length at 5 years. Okay, and then here we see that we had 177 spheric eyes. This reminds me, shoot. We didn't split the file. We have dependence on our eyes. So let's try that again. Go down, split file, compare groups, eye. Okay. Analyze, general linear model, univariate. Everything nicely stays where it was for us. And we run it again. And we're going to delete this first one. Highlight it, press delete. Okay, now what do we get here? Now we have a left eye and a right eye. And we have aspheric, spheric good control, spheric poor control, and the number of people. We see that everything's significant. The ones that we're concerned about significant is the baseline variable, which shows that it's to our advantage. We've accounted for a significant amount of the variance with the baseline. And lens type 2 also accounts for a significant part. Okay. Now let's look at our parameter estimates. Now notice that up here, as I mentioned before, The advantage of the lens type as a discrete variable in analysis of variance is that it figures out the factors for you. Whereas in a regression, you have to create these dummy variables, and SPSS does that automatically. But here's the coefficient. For the left eye, it's 0.978. For the right eye, it's 0.975. That's so close to 1, which means a unit increase in baseline leads to a unit increase in AL5. Okay, so down here we get the estimates. Here we have all the means. And one of the things that you notice that's a big difference from just doing the one way, if you remember what things were before, is that the aspheric and the aspheric good control are very close to each other. Now, it probably would have been a good idea for me to do descriptives here because you would see the big difference between these two. The estimated means are based on this regression model. And when we come up with the estimates, we use the baseline. It's basically the mean baseline for all the left eyes and the mean baseline for all the right eyes. And that's plugged in to the x value on this coefficient. So it's important to know how to plug these in and get your answer. But today we're talking about the spreadsheet. So I'm going to get this little guy out of the way, maybe. Okay. Now what we want to do is we want to copy stuff that we need into our Excel spreadsheet. First thing we need are the means. Just going to copy, and there's two options for paste here. You can do Control-C, Control-V. Control-V is going to give you this one, but it has merged cells in it. It's much easier to use the second one. Now, one of the things you'll notice is that under the means, we have a whole lot of letters in here. And so I'm going to backspace those. Oops. Get rid of those little letters. Because right now, Excel is seeing these as text fields, and we needed to see them as number fields. Okay, notice they shifted from the left to the right, justified. Okay, now before, when we have calculated effect sizes and confidence intervals, we have used the standard deviations and standard errors from the descriptive statistics. Those no longer apply here. We're going to use the pooled standard error and the pooled standard deviation from the analysis. And that is up here. And basically what we want to do is copy this into our file. And then, oh, there is one more thing we need off of that. We need to know the numbers. We don't really get, this doesn't tell us how many people were in each sample. This doesn't tell us how many. This square right here tells us how many people we have. We need that. And notice that the left and right eyes will line up with the left and the spheric, and so forth. So you never know quite where the end's going to go, but I'm going to guess right here and paste, and I did that correctly. Now we want to get rid of some columns there, so we end up going to delete, shift left, and now we have the sample size lined up next here. We're going to need the sample size because the standard error is the standard deviation divided by the square root of n, and these are our n's. Now we don't need our output anymore, so we may as well look at the whole spreadsheet. Okay. Okay, so now we have our means, our groups for each eye, and the number of subjects in each group. Now, what we want to do is calculate or figure out, first let's do standard or effect size. So effect size, you need difference between two means divided by the average standard deviation. Well, in analysis of variance, there is the assumption that all the variances are equal. And if you remember the idea of the analysis of variance and the F statistic, say right here, we have the F statistic. This 243 comes from dividing the mean square for the between groups, which is 37.8, and the within groups, which is 0.155. So that's numerator, denominator. The denominator is the estimate of the within subjects. Here it's just called error or mean square error. This doesn't show up very well, but mean square error. And that's the variance. It's the pooled variance, so it's kind of the average variance of the three groups. Now, standard deviation is just the square root of the variance. So we come over here, go equals square root of variance. And rather than taking the average standard deviations from all the descriptive statistics, we just take the square root of this. Now, this is very different from the average of the descriptives, because the descriptives do not partition out the baseline variance, the variance due to the baseline axial length. Notice that's a huge, 1159 is the F ratio, as opposed, that's like 1159 units away, standard error units away from the null hypothesis 0. You know, you usually think of a person not being normal as 2 standard deviations away. Well, this is 1159 standard errors away from 0. So that's a big part of the variance that's going away. And so this error here is a lot smaller than this average variance, this within subjects. This is after you've taken away the differences at baseline. The differences are much smaller than in the straight analysis of variance. Nothing else. So we can do the same thing, copy down here with the right eye. We see we get two average standard deviations, 39 and 41.6. So these are the values we use for calculating effect size. So we do it just like we were doing it if we were going to do it straight out. We have equals, parenthesis. We're going to use spheric as our control. So we have the good fit minus the spheric divided by our standard deviation, and we're going to hit F4 to give that lots of dollar signs so that it fixes, and we can copy down. Now you only copy down 2 because the next guys are based on this standard deviation here. So let's copy these values, paste down, and we'll highlight on this first one. Actually, I should have done that first. So this guy comes down here. And then copy, paste.
Is that divided by the average?
This is divided by the average standard deviation. So this is the standard deviation for each one. So it's 24.9 with a standard deviation of 0.39. And it's a 0.39 after you have taken out variability due to baseline. It's a much smaller standard deviation than you have if you don't consider removing the baseline variance.
Dr. Hayes, when you divided by with the standard deviation, did you put in the parentheses? Because I'm not getting the value.
Okay, so here's the thing. This is not correct yet.
Okay.
Because so this is actually, some people have done this on their homework and they really get it wrong. Because if we look to see what we're looking at, we're taking these two means, the difference between them, and we're dividing by this standard deviation. We come down to the next one and we're comparing the two spheres. And we're still within range. But when we come down to this one, we're out of whack because we're comparing spheric and the one from the right eye over here. So we need to move that guy up there. And so now we have the aspheric versus spheric good versus spheric bad, and spheric bad versus aspheric. And so now we're going to copy these, copy and paste, but we have to go through each one of them to put this correct standard deviation in. So we slide that down. It's sort of a not the smoothest thing in SPSS or in Excel to use, but it's still kind of better than doing it by hand in a calculator. Now let's look at these. This first FX size is 0.027. Well, that's a pretty trivial difference. 24.91, 24.92. In other words, for the left eye, the spherical good fit people were basically the same as the aspheric. It's similar down here, though you get a little bit of a difference. The aspheric was a tad better in terms of not growing as much as the spheric good, but from a clinical perspective, it really didn't make much difference. But if you look at the spherical poor fits, those effect sizes compared to either the spherical good or the aspheric, those were huge differences. So the spherical poor fits did very, very badly. Their eyes just were uncontrolled in terms of growth. The spherical good fits were good, and we'll later we'll try and figure out if there are baseline characteristics that can predict whether a contact lens, the spherical kind, is going to work or not. And it turns out we're able to predict that very well. Yes. Well, why don't you just... All right, so now we have computed the effect size, and we see that there's a pretty good difference. Now, it'd be nice to graph these results and show where we are. So sometimes people like to just do a quick and dirty one where they highlight and it's all one color down there with the left and right eye. I think it would be better if we compared the left and right eyes together so you can see what their relationship is. So instead of doing this, we're just going to go to the top three and highlight those, and over to the means and highlight those two. I'm going to insert bar chart, move that over here, and one of the things I always like to, well, let's not do that yet. Okay, so now we have the left eye. So let's go to select data. We're going to edit the first one. We're going to put in left eye. And then we're going to add a series. It's going to be, actually I'm going to click over here, right eye. And the values are, oh,
Do you have the option like this?
why is this doing this to me? Edit. There we go. Now you can see what our means have shown, that the aspheric and spheric are pretty close to each other, or the aspheric and spheric good are close. The eyes are close to each other, as are the aspheric and spheric, and then the spheric poor is just way worse. But it'd be nice to put confidence intervals in here. Now, we want to add confidence intervals. We're going to do our 84% confidence intervals, because non-overlapping error confidence, or 95% confidence intervals are significantly different at p less than 0.05. And overlapping error bars are not different, are greater than p of 0.05. So we have our standard deviation here. We have our sample size here. And so the standard error, so this is effect size. We need standard error. The standard error is this, whoops. The standard error is the square root of standard deviation, F4 for dollar signs, divided by, oh, I did that wrong, sorry. Sorry. It's the standard deviation divided by the square root of n. Oh, and let's hit a 4 there. Give our dollar signs. Now we'll copy down these next three. Okay, why is it not like that?
Because you need to copy.
Oh, for Pete's sake, I put the dollar signs on the wrong one. Okay, let's come up here. Try again. Okay, let's copy that. Okay, now notice we use the same standard deviation, but there is a slight difference, and that's due, of course, to the sample size. Now we'll copy these three. And we'll come down to here. And we'll move that down there. Down there. Down there. All right, now we have the standard error. Now we want to, confidence interval is mean plus or minus t times the standard error. We're just getting confidence bars, so we want to use only the t. We don't need to mess with the mean. So we will, let's just compute the t value first. And that's going to be equals t inverse. And we want 84, so that's going to be 0.16, the probability. It's the tail of it, 0.16. 0.16 plus 0.84 is 1. So we're 1 minus the 0.84 to get 0.16. And the degrees of freedom are n minus 1. And there's our t value. That we can copy straight down, because this one down here is this degrees of freedom, and the t inverse stays the same. Now we want to find out the 84th confidence interval, just one side of it, equals t times standard error. That we can copy down. So this is half a bar, the whole error bar from the mean plus and the mean minus is the same gap. Now let's come over to our graph. Let's highlight the blue, and we're going to go to design, add a chart element. It's going to be error bars, more error bar options, custom, specify value, and it's just the top three. For the negative error, it's the same top three. Click OK. That gives us our confidence interval there. We do the same thing with the right eye. Add a chart element, error bars, more error bar options, custom, specify value. Now it's the bottom three and the bottom three. OK. Now we see we have overlapping on the eyes. Now let's, just for the heck of it, go back to our SPS output and where's our SPSS output? Let's look at our comparisons, our pairwise comparisons. And ask the question in the right eye. Notice that, so we said when we looked at effect size, there was no difference up here. And but this one had an effect size of 0.2, which is a small difference, not clinically relevant. But let's look and see. I want to point out they clearly, this set, or the right eye here, overlaps this one. So even though it's 0.2 effect size, this chart says they're not significant. And if we look at the right eye, aspheric compared to good control is 0.25. They're not significant there either. So our overlapping error bars are consistent with our least square significant tests over here, which is what we want to show. One thing, these skinny little bars, I'm not really been a big fan of that. So what I like to do is format the data series and gap width. I'd like to make that down around 50%. Now, unfortunately, we still have these pretty anemic error bars, but that's what they are. The other thing you can do is mess with the colors a little bit. You can increase transparency so that you can see the bottom of these bars in the blue a little bit better, or you could also change the color. Yes, question. What? Ask your question.
When I was copying this one, the standard deviation is always copied like this 4.99. So.
Let me get this. Wait a second. So one final note about error bars. These are really little. When we just did the one way, they were much bigger. The questions are different. These error bars are based on which of these guys are different based on adjusting for the baseline covariate values. If you don't adjust for baseline, you get big variability in here. So the differences between subjects, there's a lot more noise if you don't adjust for what people's baseline error is. Because at baseline, the people are really different. And so if you start from that point, it's kind of comparable to when you look at the change over time. But this is a much better method than that because it takes into account the starting value. Whereas just change over time, the changes can be different for a number of reasons. This looks at that and gives a much cleaner answer. So you directly compare the means at the end. So you're comparing this guy to this blue to this blue. I guess I'm not convinced that looking at this figure it's best to put the left and right eyes together because they do kind of get in the way a little bit. Also, I notice I don't have a legend on here, which I did give myself the opportunity to have. So here we have left eye and right eye defined. Alright, and that's it. That's how you make error bars and test effect size. The big key here is you use the mean square error term, this guy right here, the mean square error term, as the estimate of the pooled standard deviation. The square root of that is the pooled standard deviation. And that's it. Thank you.